Okay, in the first part of this video lesson, I tried to introduce you to some of the general concepts and terminology and give you some examples to think about. Now we're officially starting section 10.1, scatter plots and correlation, and we'll talk more in detail about how you go about making those scatter plots and calculating that R and things like that. So here's the situation. You have two variables, and we can call them X and Y. So X stands for one of the variables and Y stands for the other one. And you suspect that those are related somehow. So you get some data. You obtain a list of several values for X and corresponding values of Y that go with each one. Here is one example. I stole this out of the textbook. An emergency service wishes to see whether a relationship exists between the outside temperature, how hot it is outside, and the number of emergency calls it receives for a 7-hour period. The data here are shown. So basically, there's 1, 2, 3, 4, 5, 6, 7 pairs of numbers here. In each pair of numbers, the number on top is the temperature on a particular day, and the number on the bottom is the number of calls that emergency service received on that day. So there was one day when the temperature got up to 68 degrees and they got 7 emergency calls. And there was one day, the one on the end there, when the temperature got up to 101 degrees and they got 13 emergency calls. So we want to know, is there a relationship? Like maybe on hotter days, they got more calls to the emergency service. So that's our data. That's our values for X and Y, X being the temperature and Y being the number of calls. So to make a scatter plot for a set of data like this, you would plot a point, X, Y, for each pair of values. Now, if you're used to drawing graphs in algebra where you graph an equation, you may be thinking about, okay, once you plotted the points, you draw a line or a curve through them. But here, don't connect the dots. Don't expect them to line up in a nice straight line or other obvious pattern. We're just drawing the dots themselves at this point. And then once you have all the dots in place, the idea is you might be able to look at that and get some idea what kind of relationship, if any, there is between your two variables. So if we do that here for this set of data, there's going to be 7 dots on the graph, one for each pair of numbers. So each one of these, you go over to whatever X is and up to whatever Y is, and you put a dot there. So right now I'm pointing to the dot for 68.7. 74.4 would be this one here. 82.8 would be here. 88.10 would be this one here. 93.11 would be this. 99.9 would be this one. And 101.13 would be this one here. So what can we tell from looking at that? Well, the dots don't line up perfectly, but they do sort of go up in general from left to right. Looks like, for the most part, the dots that are further over to the right are also further up, and the ones that are further left are also further down. So that shows you visually that bigger X's tend to go with bigger Y's, and smaller numbers for X tend to go with smaller numbers for Y. Now let me talk about that number R that we call the correlation coefficient. That's a number that measures how strong a relationship there is between two variables and whether it's a positive or negative relationship. For a sample, we use the letter R, just a lowercase r, for the correlation coefficient. So if you have a sample, some sample data, and you calculate the correlation coefficient from that, the symbol for that number is R. For a population, It's the Greek letter rho. It looks sort of like a P, but it's actually the Greek version of the letter R. So pronounced rho. So just like we use the Greek letter mu to stand for a population mean, or the Greek letter sigma to stand for the population standard deviation, we use the Greek letter rho to stand for the population correlation coefficient. So if we could have data from the whole population, everybody of the type of thing we're concerned about, if we could calculate a correlation coefficient from that, that would be rho. Normally, we don't have access to that. We're just looking at a sample, and what we calculate from the sample is R. The correlation coefficient always has a value somewhere between negative and positive 1. If it's a positive number that is close to 1, that means that you have a strong positive linear relationship between the variables. So the bigger one of them is, the bigger the other one tends to be. If it's a negative number that's close to negative 1, that means there's a strong negative linear relationship between the variables. So the bigger one is, the smaller the other one tends to be. And if it's close to 0, positive or negative, but close to 0, that means there's no linear relationship, or only a weak one, between the variables. Now, it is possible to have a relationship that isn't linear, that's some other kind of relationship. Like maybe at first, the bigger one thing gets, the bigger the other one gets, but then if the first thing continues to get bigger, the second thing comes back down. So we won't get into that. That goes beyond what we're studying in this course. But that's another kind of thing that if you dig deeper and go more advanced into statistics, there are other possible kinds of correlations besides just straight line linear correlations. But here are some examples of R's and scatter plots. Here's a scatter plot of a bunch of data where the correlation coefficient is negative 0.9. They don't line up perfectly, but they come pretty close, and they are going down from left to right, which is what you see with a negative relationship. Here's where R is negative 0.5. They still go down from left to right, but they don't line up nearly as well. They're kind of scattered all over. They're really scattered all over here. Here is where R is 0, which means there's no relationship at all between X and Y. X can be big or small, and that doesn't tell you anything about what Y might be. Here's what it looks like where R is positive 0.50. Here's one where R is positive 0.90. And here's one where R is 1, which is the biggest it can possibly be. And in that case, the dots do line up exactly in a perfect straight line. Now, here is the formula for the correlation coefficient. This is how that R number is calculated. And if you think this looks like a big, ugly, complicated mess, I don't blame you. I am going to explain how it works, but I'm also going to explain some other ways you can get R without having to do all of this work yourself. But this formula has a whole bunch of these sigmas in it, and those stand for the sum of a bunch of things added together. Like right here where it says sigma x, that means you take the sum of all your individual x values all added up together. So to use this formula, you need to know what all your x's add up to and what all your y's add up to. You also need to know what each x is squared and what those add up to. You need to know what the y squareds add up to. And then for each data point, you need to multiply x times y and then add those up together. And the n's in this formula stand for the number of data pairs. So that would be your sample size, how many pairs of numbers you have in your sample. You can also do this fairly easily using Excel, and I'll come back and show you how that works in a minute. And you can also do this on a graphing calculator. But here's how you would do it using this formula. Here I've got my data for X and Y, and for each data point, I've calculated three other numbers. X times Y, so like 68 times 7 is 476. I've calculated X squared, so like 68 squared is 4,624. And then Y squared, so 7 squared would be 49. So for each of these 7 pairs of numbers, we've got a number for X times Y and a number for X squared and a number for Y squared. And then all 5 of those columns got added up. All 7 of those X's add up to 605. All 7 of the Y's add up to 62. All 7 of the XY's add up to 5,535, and so on. Then when I plug numbers into that formula, N is 7. The sum of XY is 5535 minus the sum of X is 605 times the sum of Y is 62. And then that's all over the square root of, and then there's 2 sets of brackets under the square root sign, right up next to one another because they're being multiplied. So inside the first set of brackets, we have N, which is 7, times the sum of X squared, which is 53,219, minus the sum of X squared. Notice the squaring outside the parentheses, so that means take 605 and square that number. Inside the second set of brackets, we have N, which is still 7, times the sum of Y squared, which is 600, minus the sum of Y, which is 62, and then that gets squared. So here's what it looks like with all the numbers in place. This is what you would actually put into a calculator if you were calculating R directly from that formula. Let me show you what that looks like. I need parentheses around my numerator, so it's parenthesis 7 times 5535 minus 605 times 62, close parentheses, divided by, and now the denominator is all under one big square root sign. So the square root of, and I'm going to put parentheses around this whole thing, and then another set of parentheses just for the first part, the first bracket. And then inside that double parentheses, I've got 7 times 53219 minus 605 squared, close one set of parentheses, times, now I open another set of parentheses, and here I'm going to type in the 7 times 600 minus 62 squared. Close that set of parentheses, close the big set of parentheses for everything under the square root sign, hit enter, and this comes up as 0.811368, and so on. So that's my correlation coefficient, as calculated on the calculator. I told you could do this on Excel, and this video is running a little long, so I'm going to end this one right now and come back in the next part and show you how you can do this on Excel. It's a lot easier than trying to put this formula in, I think, especially if you don't have this all worked out ahead of time and you have to do all of this yourself. But I'll show you how that works when we come back in the next part of the video.